is swept at a constant rate from the sun to the planet, area is swept out by the line at a constant rate. Okay. So that's an interesting law because it tells you, once you know what the orbit of a planet looks like, it tells you how fast it's going to move on that orbit. Okay, so let me explain again. So this law says, maybe the sun, let's put the sun here at the origin, and let's have a planet. Well, the planet orbits around the sun, in some trajectory. So this is supposed to be light blue. Can you see it as different from white? No. Okay. Me neither. Okay. Doesn't really matter. So the planet moves on its orbit, and if you wait for a certain time, then a bit later it will be here, then here, and so on. Then you can look at the amount of area, inside this triangular wedge. And the claim is that the amount of area in here is proportional to the time elapsed. So in particular, if the planet is closer to the sun, then it has to go faster. And if it's further away from the sun, then it has to go slower, so that the area remains proportional to time. So it's a very sophisticated prediction. And I think the way he came to it was really just by using a lot of observations and trying to measure what things were, what was true, what wasn't true. But let's try to see how we can understand that in terms of what we know today about mechanics. So, in fact, what happens is that Newton was quite a bit later. I mean, that was the late 17th century instead of beginning of the 17th century. So he was able to explain this using his laws for gravitational attraction. And you'll see that if we reformulate Kepler's law in terms of vectors, then, and if we work a bit with these vectors, we're going to end up with something that's actually completely obvious to us now. At the time, it was very far from obvious, but to us now, it's completely obvious. So let's try to see what does Kepler's law say in terms of vectors. Okay, so let's think of what kinds of vectors we might want to have in here. Well, it might be good to think of maybe the position vector and maybe its variation. So if we wait a certain amount of time, we'll have a vector delta r, which is the change in position vector over a certain interval of time. So let's start with the first step. What's the most complicated thing in here? It's this area swept out by the line. How do we express that area in terms of vectors? Well, I've almost given the answer by drawing this picture, right? If I take a sufficiently small amount of time, this grayed region looks like a triangle. So we have to find the area of a triangle. Well, we know how to do that now. So the area is approximately equal to 1/2 of the area of a parallelogram that I could form from these vectors. And the area of a parallelogram is given by the magnitude of a cross product. Okay, so I should say this is the area swept in time delta t. And you should think of delta t as relatively small. I mean, at the scale of a planet, that might still be, a few days, but small compared to the overall trajectory. So now let's remember that the amount by which we moved, delta r, is approximately equal to v times delta t. Okay? I'm just using the definition of a velocity vector. So let's use that. So it's again approximately equal to r cross v magnitude times delta t. I can take out the delta t, which is a scalar. So now what does it mean to say that area is swept at a constant rate? It means this thing is proportional to delta t. So that means, the law says, in fact, that the length of this cross product r cross v equals constant. Okay. R cross v has constant length. Any questions about that? No? Yes? Yes, let me try to explain that again. So what I'm claiming is that the length of the cross product r cross v measures the rate at which area is swept by the position vector.